So we're at the point of our series here where we do get to talk about applications of what you can do with this. Today we're going to discuss how you find the volume of certain figures and how you do it with discs and washers. Now I know you're probably thinking discs and washers, what in the world does that mean? What do those little washer donut looking things and discs have to do with finding volume or even integrals? But I'm going to show you that it does. It actually does. So here's the idea. I'm going to try to build this up for you so you kind of understand where this stuff's coming from instead of just give you the formula. Just like I did for derivatives, just like I did for integrals, I'm going to do the same thing for volume. You follow me? Now, do you remember the Riemann sums where we took a whole bunch of rectangles and found arbitrary points and then added their areas together?
Yeah, I did.
Okay, we are going to do the same thing with the volumes. You ready for it?
No.
So I'll try to break it down. Again, it's not going to be too bad, but we're going to talk about first the volumes by slicing. And what that means is, what if we did the same thing we did for areas? Areas, we had this figure, the one I draw all the time, and we sliced it up, right? And we made lots of little rectangles. We made lots of rectangles. We added up the widths times the heights of all those rectangles, thereby getting the areas of all the rectangles. That's basically the idea that we're going to use only on a volume type application. So let's talk about that. So right now we'll discuss the volume by slicing.
Is it different for liquids?
Solids as a solid figure.
Okay.
Solid figure. Yeah, we don't mean a piece of cake is different than Jello. Okay?
That's what I was thinking of.
No, that's not what I mean.
Different?
Jello goes like this. Pudding like this. Cake sticks together. No, not that kind of solid. I mean, like you have this three-dimensional shape that doesn't have any holes through the middle of it. Okay, that's a solid. So it could be liquid. It doesn't matter what it is. It's contained, and it's not changing shape. You understand?
Mm-hmm.
That's solid. No holes in the middle of it either. So here's the deal. Let's take some random figure that I'm going to create right now. That. So that's maybe the side view of this figure. And let's make it three-dimensional. Is that three-dimensional enough for you? Can you see it okay? Okay, so that's my figure. Here's the idea. What if we could take and make slices of this thing? If we can find the volume of a slice, then we should be able to add all the slices together and find the volume of the whole figure. Do you see how this kind of parallels the area under a curve idea? So we're going to try to find slice. Let's make a slice. So some random slice of this thing. I'll take it here. You guys having a hard time doing the whole three-dimensional thing?
Mm-hmm.
Okay, yeah, it's kind of difficult. You get used to it after a while. Do you see the slice I'm trying to portray right there?
Mm-hmm.
So basically this is a weird shaped cake. You did a bad job on your cake. But we'll take two planes, right? Two pieces of paper or laser beams or something. So we have this nice slice of this cake and you're going to serve someone your crappy made cake. You got it? No icing even. Kind of a host are you? But anyhow, that's what we're going to do. So our idea is, let's cut this into thin slabs, we'll call it, a slicing or a slab. And we're going to try to use a Riemann sum, use our sums that we used before, to set up some sort of integral. So this is our idea. I'm going to write it out. I'm going to try to walk you through this so you understand where it's coming from. So idea. Cut into thin slabs. Then we'll use a Riemann sum or summations. So we'll use our summations to set up an integral. You make a little side note here. This is much, much like the area problem. Very much, only it's in 3 dimensions. So in order to do this though, well, how do we find, I'll kind of break this down so you understand it. Let me start over then. Do you understand what's going to happen with this slab? What's going to happen with that slab? If it's much like the area problem, what's going to happen to that slab?
It's going to get very, very thin.
Very, very thin. Very thin. Now think of a volume. A volume area for you guys typically is base times width times height, right? But that's only of a rectangle. It's only of a rectangle. And things don't have to be rectangular. So I'll say it this way. Volume is typically the surface area times its length. Does that make sense? So whatever the surface area is, or in our case, the cross-sectional area times its width. So if I found the cross-sectional area, so I cut it this way. I take my slab out. I turn it towards you. That's the cross-section. Can you picture that three-dimensionally? You cut it like here. I'm cutting it. I pick it off. I turn it this way. What you're looking at right now is the cross-section. If I take the cross-sectional surface area times its width, that's going to give me a very good approximation of its volume, right? If the width of that slab goes like this, that gives me an exact interpretation of that volume because it has very little width. Does that make sense to you? Very much like finding the area of those rectangles and say, hey, I can find the area, now take it to 0. That's now an exact area if I add them all together. And that's what we're doing here, except in terms of volume. So in order to do this, we need to find the area of the cross-section. To do this, I mean that, we gotta find the area of cross-section. Well, in general, we would do this. I'll try to break down so you see where all this stuff's coming from. If we had just a basic, like, rectangular prism, if we had just a basic, do you see the rectangular prism? If we had just a basic rectangular prism, and it was, I don't know, going through some axis. Like that. Like maybe the x-axis. If we wanted to find the cross-section, well, what we would have to do is take a slab, or take a slice to find the area, and we'd slice it like this. Oops, that's way off. There we go. We do some sort of a slice. Now tell me something. If this distance is x, it's on the x-axis, and this distance is, let's say, oh, what did I call it? I think I called it y for that. And this distance is y, and this is z. Could you find the surface area of the cross-section? Would it have anything to do with x? What would it have to do with?
Y and Z.
Just Y and Z for the cross section. So check this out. If I asked you to find the volume of this whole thing, here's how you do it. You'd probably say, oh, well, I know the volume of a rectangular prism. The volume of a rectangular prism is just the base times the height times the width. So basically, it's the Y times the Z times the X. Do you follow me on that? Now I'm going to kind of prove to you that this is the cross-sectional area times the length. Do you agree that this is the volume of this figure, no matter what? What's Y times Z? Y times Z is the surface area of the cross-section. That's what that is. So basically this says, oh, that's the surface area of the cross-section times X, the length. So this is surface area of cross-section. And that's the length. Well, now here's the idea. If that's the case, then what we're basically doing here is making a whole bunch of these things. Do you see it? Making a whole bunch of those things and then adding up all the volumes. Very similar to making rectangles for areas, we're making rectangular prisms for volumes, and we're going to add them all up. So what the idea I needed to get across to you was that a volume is basically a surface area times the length. How many people feel okay with that? Surface area times the length gives you the volume. Good deal. Now we can solve any volume where the solid is bound by planes that are perpendicular to the x-axis. Here, let me explain it to you. If this was like this, and it was not straight up and down, could you cut it into slabs? It wouldn't work right. It wouldn't be a slab to start with. That would be a problem. Here, slabs. Yes, slabs that are perpendicular. That's very nice and easy. We can do that. So now we've got it down to, if our sides are perpendicular to the x-axis, we can start cutting it into slabs and approximating by rectangular prisms. Do you see the point? If they're not perpendicular to the x-axis, then this method's not going to work for us, and we have to do something else. But if the sides are perpendicular, we're good to go. So now we can find the volume of any solid that's bound by planes that are perpendicular to the x-axis. You know, I probably should say at points A and B. So at where we're starting and where we're stopping. So if we only wanted to find the volume between here and here, it would just have to be perpendicular at those points. The rest of it really wouldn't matter, just like the area under a curve doesn't matter if it's undefined. It's just between the two intervals that we talked, between the interval that we talked about. Are you following me on that one? So be at points A and B. Basically where you start and where you stop. Would you like to see how to make this integral up? It's kind of cool. It's kind of fun. I think you'll enjoy it. There's going to be a lot of picture drawing. Well, to start off with a lot of picture drawing. You ready for it? Sure. I'm going to go back to this because I really don't want to draw that anymore. Are you guys all right with that? I don't want to draw that. It's kind of annoying. So let's just say that from this picture, I'm going to go back, and you already know the idea. I'm going to be cutting a whole bunch of slabs out. You know, maybe I will redraw it. Darn it. Yeah, I'll redraw it because I have to talk about other things. Plus, I'm going to reverse it because it's easier to draw the top of it at an angle. So let's say that I do, same idea, but I do this one. a little off, isn't it? And I'm going to try to give you every step along the way. So my first goal, I'm going to cut into slabs. Okay, slabs. Okay, there's one. Now I'm going to cut another one. There's two. I'm going to cut another one. You see my slabs? Yes, no? I'm going to cut all of these, so dot, 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 all the way down my figure. I'm going to cut this into a whole bunch of slabs, and I'm going to do it this way. I'm going to cut the slabs so that they're the same width. This is going to make it easier to add together. Just like we did with the area problem. Hopefully you're seeing the similarities between this and the area problem. So I'm going to cut into slabs the same width. How did I represent the width of my areas, and how am I going to represent the width of my slabs? Yeah. Do you remember that we used delta x to represent the width of that little sub-interval? So I'm going to cut this into slabs delta x wide. So all these little intervals, all those little cuts, those slabs are all delta x wide. You still so far so good? Yes, no? Okay. Now, would you mind if I took one of those slabs and just kind of blew it up? Not like, but like made it bigger? I'm guessing some of you are wishing we could just blow it up, huh?
Yes.
No more math. Ha ha ha. Too bad for you. This is two-dimensional. You cannot blow it up. Maybe you could, unless you want to. Anyway, I'm going to take one of these guys, one of these slabs, and make it quite a bit larger. Oh, ran out of space. Let me redraw. Pretty close. Do you see it? What I'm trying to get across to you? Oh, this is going to be difficult. Not too bad. So I've taken one of these slabs right here and I've made it just bigger so you can see a better picture. Now, can you remember what we did on the area problem? I cut each one into intervals. What did I do within each interval? Someone tell me, what did I do? It wasn't necessarily in half, but you're on the right track.
Arbitrary point.
Arbitrary point, great. You guys both had it at the same time. So I'm going to pick some random point. I could put it in the middle. It's going to look like it's in the middle, but it doesn't necessarily have to be in the middle. Explain to me why the arbitrary point doesn't have to be in any particular point.
Because you're taking the limit.
It's going to do that, yeah. So wherever it is, it's going to be within there, right? But it's going to be so darn close to everything else that it's not going to matter where it is. So I'm going to pick an arbitrary point. What did I use for arbitrary point? Do you remember? xk dot or c sub k, one or the other. I'm going to use xk dot because that's what I grew up with. So arbitrary point xk dot or c sub k, doesn't really matter, on the interval. Okay. So that means that down here I'm going to go, all right, on my width, this is my subinterval, that's delta x. This width is delta x. Do you guys understand that? That's delta x. On this, well, let's see, delta x, all the way at the bottom, delta x. On this little subinterval, I am going to pick some arbitrary point. Now, Sarah said the middle. I'm going to put it in the middle. It doesn't have to be there. Just so we can see it easier, I'm going to pick some random arbitrary point, xk dot. Now think back to the area. On the area problem, when I found my xk dot, what did I do with that xk dot? Remember the area problem? You had the width, right? The width was very easy. What were you missing?
Height.
What did I do with the xk dot?
Plugged in the function.
And that gave me my
Height.
height. Now what I'm looking for here, please watch this. I hope you're seeing the parallels here. What I'm looking for here is not the width. The width is going to be easy. The width is going to be from A to B because it's bound. It's bound by planes like this. It's going to be from A to B. This is not what I'm worried about. What I'm worried about is this part. This part is my cross-sectional area. So what I'm doing here, the width is easy. The width is delta x. In general, it's going to be from A to B. That's easy part. In an integral, that's very easy. A to B, no problem. What I'm caring about is how in the world do I find the cross-sectional area? Because when you think about it, this is not a rectangular prism. This is going up at an angle, right? So what I need to do is find some place to get the cross-sectional area. The place I choose to find my cross-sectional area isn't this far right one or this far left one necessarily. It's some arbitrary point, xk dot. We just talked about how xk dot really doesn't matter because I'm going to smash them together. So xk dot simply allows me to find my cross-sectional area of each subinterval. Say that one more time so you get it. Arbitrary point. What we're doing with the arbitrary point is finding the cross-sectional area right there. That's the way that we're going to find the cross-sectional area, surface area. That way I can multiply it by its width. Again, the arbitrary point doesn't matter because when I take a limit of it, it's all going to smash together anyway. So this point says, hey, find cross-sectional area at xk dot. So pick an arbitrary point xk dot on each subinterval and find cross-sectional area at that point. Cool. So that means to me that I'm going to go down here and I'm going to do this. Not bad. My purple line that goes around that's my cut at xk dot. Do you see that what that's going to create is just some surface area for me? Yeah, you know? So we're going to find the cross-sectional surface, that's cross-sectional surface area at that point. Again, it doesn't matter where it is since delta x is going to become really small. It doesn't matter. So let's see. Well, we're about ready. We're about ready. Can I work over here so I don't get all bound up? You don't want to get bound up in calculus. Calculus constipation, then you're bound to get a brain fart. Get it? That was pretty funny. Come on, brain fart, lose it on it. I just made that up. That deserved more than your courtesy. That was good. Just think about that later. Watch the video again. It'll be on. I'll leave it on there for you so you can enjoy that over your 2-day break. What's V sub k?
Arbitrary point.
Nope, that's xk dot. What's V sub k? What's V? Volume. Volume sub k means of whatever little interval I'm talking about. You get it? So this is every little interval. So the volume at the first interval or second interval is going to be equal to, well, the area at xk dot. Times what do you think? Times what? What am I doing up here? How do you find volume again? How do you find volume? What are you doing for volume? We're beyond that. Yes, it's length times width times height for a rectangular prism. We do not have one of those here. Surface area times width or length. Yes, that's what we're doing. So the surface area is the area at xk dot. Do you get it? That's what I'm trying to represent here. The area at xk dot, the surface area, times the width. How long is the width? Very good. Delta x. This is cross-sectional area times length. Just like we thought of it. Cross-sectional area times length. Now, how many intervals does this stand for? One arbitrary interval. Very good. So this is just one interval. How do I find all of them? So basically, I'm just talking about one slab right now. How do I say I want to do all the slabs? A sum. Let's add them all together. So if we say, okay, this is one slab, then this, if I drop the k, I say, oh, if I want more than one slab, I'm going to have to add them all up. Starting at the first one and going through the nth one. That should look familiar. It's just like area right now. Only inside of it says, oh, find the area at xk dot times delta x. Hey, that's just for each one. What this says is, take every slab that you have, every slab, find a random point for each slab, find the area of the cross-section at each random point, multiply each one of them times its width, and add them all up. That should give you an approximation for the volume. Approximate volume. Okay, now, use your calculus. How do you make it better? Very good. Did you hear him over there? He said take the limit as n approaches infinity. That's going to say, instead of a finite number of slabs, which would be a pretty good approximation, make it an infinite number of slabs. If you pack an infinite number of things into a finite space, it moves it really close to zero. It doesn't become zero because you have to have some sort of length, don't you? If delta x were zero, you get a volume of zero. That wouldn't make any sense. So you have to have something there. But it's so small that it's not going to be an approximation anymore. It's so small that that's going to be exactly what the volume is. So yeah, exactly. Take a limit. So this is an approximation. How I make it exact is I go, all right, take a limit as n goes to infinity of this same thing that we had. And I'm hoping you can figure out what comes of this. I think I told it to you before. What's a limit of a sum? What's a limit of a sum? That's what it is. It's an interval.
So we'll be doing these through using the integral, not through Riemann sum.
Well, let's explain that in just a bit, okay? Just understand that this is going to give you an integral from where you start to where you stop, where A and B are the start and ending points of your volume, and they have to be perpendicular to the x-axis. Otherwise, you can't make slabs. Follow me? A of xk dot becomes A of x, the area function of your function, and then the delta x becomes dx. And A of x is the cross-sectional area over the interval from A to B. Would you wish I feel okay with what we talked about so far? Now, are you going to have to do Riemann sums? No. I've just proven it to you. Why would you do Riemann sums? That's way easier. Shoot, don't do that whole process. But I proved it to you, didn't I? Showed you how this all works. That way when I give you this, you're like, that doesn't make sense. Well, yeah, it does. It actually does. It says, this is cross-sectional area with whatever the width is, and you're adding them all up from A to B. That's all it says. It's just a different way to say this right here. Easier to calculate, though, because you know how to take an integral, don't you?
Yes.
Awesome. By the way, does it have to be along the x-axis? Oh yeah, did you have any questions on this? I don't do it on purpose, probably.
I think I did redraw it.
Yeah, no, of course we do. See me after.
I tried.
We could probably do the same thing according to the y-axis, except instead of being perpendicular to the x, it'd just be perpendicular to y. If you turn your head, it's got to be that way. So we do the same thing with respect to y. So in our case, the volume would equal, hey, where would you start, where would you stop? C or D?
C to D.
C, small to D. Whatever the area of the cross section was according to y. And then you have D. Yeah, that would be it.
That's DX.
Just checking, making sure. Sure you're awake. Good. Yeah, dy. It's such a habit to put the dx, isn't it? You always want to put that. But watch your variables. So basically what this says in English is the volume of a solid is found by integrating the cross-sectional area from A to B. That's what that says in English. The volume is found by integrating the cross-sectional area, the area of the cross-section of a three-dimensional space, from, well, C to D in this case, or from A to B. Would you like to see an example of how this is done?
Yes.
It's kind of cool. It's not too bad. Let me give you this one. Sorry for those of you who are not three-dimensionally inclined. These are probably really hard to draw, so my bad. Well, actually, you're bad. I'm not the one screwing up. I really am kind of a nice guy out of class, but you wouldn't know it, would you? All the jerk things I say. This is a 1 here and a 5. 1 and 5. Now, would you like to see how this is done appropriately? Firstly, we're going to have to find, now this is a kind of a, these are simplistic examples to start with, just so you know. Very simple. Why are they very simple?
Why make it complicated?
I'm going to make it complicated, yes. Why is this simple? Does the function ever change?
No.
It's a uniform function the whole way, okay? It's going to be uniform aerial cross-section, cross-sectional area the whole way through. So what we know is that the volume is going to be the integral of the cross-sectional area from where the function starts and from where the function stops. Now, first thing, does this qualify? Do I have planes that make 90 degrees with the x-axis? Or the y-axis, one or the other? Yeah, this is 90 degrees and that's 90 degrees, so that's great, that's what we need. Can you please tell me what's the area of the cross-section? How are you getting that?
Well, you got a circle at one end, and that's your.
Sure. So if we cut this thing right down, if we cut this and then turn it and look at it, that's going to be a circle. Do you see the circle? So the circle is pi r squared. Cool. Okay. in our case, what is it? How much is the pi r squared? What's the r?
The radius.
Sure.
One.
The radius is 1. The radius goes, well, can you see the radius is 1? Diameter is 2, radius has to be 1. So for us, it's pi 1 squared. Pi. Would you all agree that the cross-sectional area of this figure is simply pi? And it doesn't change. There's no x involved in it because it doesn't change. It says it's a constant. It's just circles stacked up right next to each other. So what our theory says here is that the volume should be equal to an integral from where it starts. Where's it start? Along the x-axis, where's it start? I'm sorry? Okay. 1 to where?
5.
Of the cross-sectional area dx. Because we're going along the x-axis. Sure, that's an x. Show of hands, how many people feel okay with this so far? Cross-sectional area, it's just the area of a circle. That's pi in this case, the radius is 1. That is cross-sectional area that's a constant. There are no x's because it does not change. If it changed, we would have x's, for sure. It'd be a function in terms of x. Now, we're going from 1 to 5 because it's where we start, that's where we stop, that's where our planes are perpendicular, no problem. Hey, can you find the integral of pi dx? Not too hard. What's the integral of pi dx? Pi x. With the little thing, that's the evaluation symbol. From where to where?
1 to 5.
So this says pi times 5 minus pi times 1. What's pi times 5 minus pi times 1?
4 pi.
4 pi. That's kind of neat. We just used, well, it is neat until you realize you can do this without calculus. But it's kind of neat that you're able to find the volume using calculus. Now, let's just be clear that this is true, because this is simply a cylinder, right? What's the volume of a cylinder? Pi r squared height. Hey, think about what you're doing, okay? Just think. The volume of a cylinder is the base area times the height. You basically stack up circles. That is literally exactly what we're talking about here. It's the area, and you stack up all the circles. That's what we're doing. Same thing. So it should work out the same thing. Volume is pi times 1 squared times height. The height in this case is really the length. What's 5 minus 1? It's 4. 1 squared is 1 times 4 is 4 pi. This might not seem so impressive to you, but getting the same answer is kind of neat, right? Now, unfortunately, these don't always happen, right? You're not always going to get that formula. Not always going to get that. Did you understand that so far, though? Now we can just take it a step further. We're still kind of basic, okay? We're going. Are we going slow enough for you?
Yeah.
You understand everything, right? Hopefully it's slow enough, man. We're going to start talking about some more unique shapes. Not just cylinders, but we're going to get some other things. So what we'll do now is say, let's suppose you have some function, and you start revolving it around an axis. Do you see that it's going to create a solid? The sweep out area is going to create some sort of a solid. You with me? Let's get a picture of those before we do anything too drastic. Let's see what they're making. And what we're going to call this subsection is a solid of revolution. A solid of revolution means the solid you get if you take some like piece of paper or solid shape and revolve it around an axis. You're going to get a solid of revolution. Let me give you a for instance here. If you took that shape and what is that shape? This. You took that shape and you revolved it around the x-axis. What's it going to make? So basically you do this, you go sweep it out. That's a horrible idea. Let's see if I can find something better. is much more, there, now you see it. Take it, revolve it. That's just creating a cylinder in space. Do you see the cylinder in space? Open right to the right page too, awesome. So this, if I did, yeah, that's going to create exactly what we had right here. This is basically a rectangle that's sweeping out an area, a solid revolution. Sorry, a volume. Sweeping out a volume. So this would create this shape. Basically, I didn't draw it very nicely, but it creates that cylinder that we were just talking about. Well, I really jacked that thing up. Forget this. Hang on. I gotta make it nicer for you guys than that. That's basically the shape that you get. What about this? What if I took that? Yeah, if I took a half circle and I revolved it, I'm not going to get a half sphere, am I?
Then you get
I get a full sphere. Which means that to get our solids, you can still deal with a function. Because if I took a full sphere and revolved it, full circle and revolved it, it'd still make the same exact shape. Actually, some people would say, well, it sweeps out twice the volume because you have twice the sides. But it makes the same exact overall shape. It makes a sphere still. So this, if I did, yeah, sure, I'm going to get globe. Not an egg. If it's a half circle, I bet hopefully it's a sphere. What if I took this figure? What would I get if I swept that around? Mm-hmm. Sure, it's going to give me a cone. Absolutely. Let's talk about one more. It's kind of a fun one. Yeah, I'll do it here. How about that? A donut. Ooh. What do you think?
So you with the hole in it?
So, a paper towel roll. You basically get a paper towel roll. That's what you get. You're going to take this solid thing and sweep it around, but there's a hole in the middle of it. So, donut, I couldn't say yes because donuts have, it's actually called a torus. They have curved sides. You can't do that. This will have the straight sides still because you're sweeping that out. It is rectangular, but it's going to have this hole right in the middle of it. So this would be basically a cylinder within a cylinder. You sweep out this, you leave this. You see the figure I'm trying to draw for you? It's that three-dimensional. The solid space is actually this, and this empty the empty cylinder in the middle doesn't contain anything. You haven't swept anything out for that. Now, the reason that we're going to go a little further is these shapes are pretty easy. These are easy. We have standard formulas for this. This would be, hey, cylinder. This is sphere. We have formulas for the volume of the sphere. We have formulas for the volume of the cone. We have formulas for this. It's a cylinder minus a cylinder. That's all that is. What we don't have formulas for, as where I'll leave you, is this. What if I said, now what I'd like you to do is take my favorite function from A to B and sweep that thing out. Now that's not a regular shape. That actually has a curved edge. So I can't use any of those geometrical principles, but what if I did that? Well, do you see the picture I'm going to get?
Kind of weird. It's really weird looking, but yeah. Oh, that's second one.
Kind of like that, isn't it?
It's a base.
Basically a vase. Basically a base. And it's also a base from A to B. Now, two questions before I let you go. Number one thing, is it still a solid? Cool. Number two thing, are the sides still perpendicular to the x-axis?
Yes.
Which is cool, which means that we're going to be able to use this stuff that we talked about to do something like this. And that's what we'll start next time. All right, well, we're going to wrap up talking about volume of these three-dimensional objects, which is a really cool idea. What it says is that if F is, firstly, continuous, and if it's bounded between A and B, bounded between A and B, and we rotate it around the x-axis, well, if you think about that picture, and it's bounded by A and B, another way to say this, by the way, if you get this on your homework, notice that you could get, instead of bounded by A and B, it could say bounded by x equals A and x equals B. Are you okay with that? X equals A and B are vertical lines, are they not? So that would be bound between those two vertical lines. Vertical lines are perpendicular to the x-axis, so if we have a continuous bounded function between A and B and we rotate it about the x-axis, it will have sides that are perpendicular to the x. And this implies that we have a solid that's been rotated around the x-axis. Using that, we can talk about our solids of revolution. We just talked about those last time. We talked about cylinders. We talked about the rectangle rotated around the x-axis makes a cylinder. We had that paper towel looking thing, right? A toilet paper looking thing, where we rotated a rectangle that was hovering above the x-axis. We had a cone. We had a sphere. We had those shapes. Now it says, well, if you have just some random function f of x, as long as it's continuous, as long as it's revolved around the x-axis in such a way that its sides are perpendicular to the x-axis, we should be able to use some method in order to calculate that volume. Would you like to find out what it is?
Sure.
It's kind of cool, and I don't think it's going to take too much for you guys really to get it. What I'll do first is draw you a picture of the revolution. So I'm going to draw this in 3 dimensions, or try to at least. Yeah, that's close enough. Feel okay with the shape, see where it's coming from? So rotating that solid, sweeping out the whole volume. Question?
So the sides that are perpendicular, the front and the back, that's what you mean?
I mean, it's the front and the back, that's
Okay.
exactly right. So
Okay.
right here, this is perpendicular.
Right.
It looks like it's got a little curve, but that's just because I want to show the 3 dimensions. But if we had this thing here, it'd be completely flat, just like a vase sitting on a table. Right? It's flat and it's flat. The plane is perpendicular to the x-axis right now. Are you all right with that? Now, questions I have for you. First question. Put something right in the middle. What's that point? Say it again. Yeah, exactly. If we have something starting at A and ending at B, the 3-dimensional space should also start at A and end at B. Now that's sure, for sure. Next question I have for you. Oh, this is a little off, isn't it? That's a little better. If I were to take this figure and I were to slice it, because that's what we're about to do, is find the volume by slicing. If I were to slice this just right in the middle, like this slice right there, what is the cross-sectional shape going to be? It's going to be a circle. Why?
In a revolution, and both sides are perpendicular.
Okay, very good. So we have a circle. You understand that, right? Now let me ask you a question. Is this some random function, or is this a specific function? Have I used like x squared? Have I used any specific function here? I just took a general curve. So my question is, if I take any continuous curve between A and B, and I revolve it, what's the cross-sectional shape always going to be? It's always going to be a circle. You understand that? If I take a shape and I revolve it, it's going to give me some circular slicing. That's kind of interesting, right? So every one of these, if I look at the slice, it's going to have a distance. What do we call that distance? If this is my shape, what do we call that? Say what? Radius, that's right. Now, what we're going to do is we're going to find the volume by slicing. Here's the idea that we came up with last time. What we came up with last time is that the volume should be some integral of the surface area from A to B across my interval. Do you remember doing that from last time? Refresh your memory on your notes or the video. That's what we came up with from our solids revolution. We said, hey, length times width times height is great, but we don't always have the same length times width times height. So what we're going to do is say, hey, let's just find the surface area of a cross-section, and we'll integrate it from A to B. What that says is that the surface area can change shapes and sizes because we have a variable in there. We just need to find a function that represents that surface. Let me say it again. We need to find a function that represents that surface area, and then we can integrate it. Integrate it is just adding up all those little slices from here to here. Do you follow me on that? So we'll slice them all up, real fine like, real nice, and then add all those things up. That's adding all the surface areas of each little slice from A to B. That's what that means. How many people feel okay with that so far? All right, that's the idea. Now we're going to get a little bit more specific. I'll walk through every step. Firstly, note that A of x represents the surface area of the cross-section. You okay with that? Area equals the surface area of the cross-section. That's what we mean there. Now, we just talked about this. This is the cool part. Oh my gosh, this is a really cool part actually. The surface area of the cross-section. What is the cross-section? What was that shape that we just talked about?
Circle.
Very good. That's pi r squared. That's a circle. Note that any time you revolve something around the x-axis, the cross-section will have to be a circle. You're not going to do this. You're not going to go revolve, square. No, that doesn't work, right? When you revolve something, you're evenly rotating it around, so it's going to sweep out a circular pattern. That's what it's going to do. Whether it's really big or really small or changes, the cross-section at one cutting is going to be a perfect circle. You follow me? And the area of the perfect circle is going to be pi r squared, whatever the r happens to be. Now let's talk a little bit more about r from here. How in the world are we going to find r? Because we would definitely need r up here, wouldn't we? Definitely need r. What is our r? Don't overthink the arbitrary point thing. We're a little bit past that. That's how we came up with this idea, was the arbitrary point at each sub-interval and then taking it to infinity, so we have very little width between there.
That's what r is. What height
It's the r is, okay, think about r as being perpendicular to the x-axis, then r is the same thing as the height of your function at any given point x, right? So that you know that your height here is just f of x. If this were some point, and now maybe I see what you're saying, if you pick some point x sub 1, then the height at that one point is f of x sub 1, or the same thing as the radius at that point. So here's what I'm going to say. If this is a circle, then the radius of that circle has to equal f of x at any point x. Yes, no? Is the radius the height of your circle at this point? The radius is the height of your circle, right? And it changes. Depending on where your x is, the radius would be here, the radius would be here. That also is exactly the same thing as the function, the height of the function. So what I'm trying to get at is, just look at the board here real quick. The height here, which is the function's height, is the same as the height here, which is the radius. Is that true? Therefore, the function equals the radius. That's another way to look at it. So radius equals the function. Well, that's kind of cool. That lets us make a substitution. If we have a sub x, which doesn't make sense right now because that's not in terms of x, is it? And we needed it in terms of x. So a of x equals pi r squared. A of x equals pi, not r, because r is not in terms of x right now. We needed to make it in terms of x. What's going to go in there? And then what?
Square.
Very good. How many were able to follow that? Hey, guess what? You're done. You're done. That is the method. Because look, what we were looking for is a of x, the area in relation to some variable x, and now we have it. This is in terms of x. What it says is, in order to find the volume by slicing, you go from where the interval starts to where the interval stops of pi f of x squared dx. And it says, you know what, it's not even that hard. It says you take your function, you plug it in, you square it, and you multiply by pi. Now someone tell me something about the pi. What can you do with the pi? You can always bring it out because that's a constant that will always be there. I show it here so you don't forget about it, but you can easily pull that out of your integral. This right here, this is called the method of disks. Why do they call it the method of disks, do you think?
Because you're making the slices in a circular object.
Yeah, which is a disk. You're basically adding up disks, circular. You're adding up disks. That's what they call the method of disks. Now, would you like to see an example?
Yes.
Okay, let's do a couple of them. First one's going to be real basic. And here's how some of these things are worded. Find the volume of the solid of revolution where I'm going to give you some function. I'm going to give you some interval. Is revolved around the x-axis. So we're going to find the volume of the solid revolution. That means we're going to be revolving something. Of y equals 3 root x on the interval 1 to 4, and that's being revolved about the x-axis. So we're going to be making some circular shape. It's revolved around the x. That means it can have perpendicular sides. It means we can do the slicing thing. If we had this, we couldn't do the slicing thing because we wouldn't be able to make circles. We have to be able to make circles for this to work. You got it? That's where the perpendicular comes in. Now also, this could be worded a little bit differently. I need you to be prepared for that. I'm not going to write it out, but you can hear the difference. This could be worded in a manner such as this. Find the volume of the solid of revolution of the area bound by y equals 3 root x, x equals 1, x equals 4, and the x-axis. Does that make sense to you? It says, take it between this function, whatever this function happens to look like, it looks like that, about, the x equals 1, x equals 4, and the x-axis. That comes up with the same exact area that you're going to be sweeping out. Do you see the point? So it can be worded differently. Don't let the wording jack you up. It's going to give you bounds, it's going to give you a function, and we're revolving that. So again, this could be written just like this, how I'm going to hopefully word it for you, or it could be written, find the volume of the solid revolution that is bound between this, x equals 1, x equals 4, those are your vertical lines, and the x-axis, that's your horizontal line. Or y equals 0 could be the x-axis as well. Feel okay with that so far? So that's the picture we're going to have. We're going to take this thing and spin it around. Now we'll go real slow and see if we can do this together. So we know that volume is some integral from a to b of pi f of x squared dx. Let's see if we can fill that out appropriately. Where is my integral going to start, do you think?
1.
Very good. Where's it going to stop? What's going to be inside of my integral, first thing? Oh yeah, you're certainly going to have a pi, for sure. That doesn't change. And then you're going to have the function f of x. Now, in our case, what is f of x? 3 root x. Very good. So we'll have 3 root x. And what do I do with that 3 root x? So you do what now? Mm-hmm. Notice how the 3 is with that root x in this case, because that is part of your function, right? You're squaring the whole function. So we have our pi, we got our pi. We got our f of x, that's 3 root x. We got our square. Don't forget the square. Let's go forget the square. Can't forget the square. Don't forget the square. You feel okay with this so far? Notice how the integrals are going to be not so bad. Well, sometimes they are a bear. I'll give you the honesty. Sometimes they're nasty. Because you're squaring functions. I mean, if I had given you like x squared minus 3x plus 4, and we had to square that, that's not that fun. But this one's going to be at least a little bit nice so you can see it, right? So don't forget to square it. What we'll get is 1 to 4 pi. Tell me about this. What happens there? Say what now? Both parts, not just the square root, but also the 3. So what are we going to get? That was pretty nice. See how nice of a guy I am today? I told you I was in a good mood. Yeah, we get 9x. See where 9x is coming from. Tell me something else I can do with this integral. Good, I'm going to pull out both, the 9 and the pi. From 1 to 4 of x dx. No substitution necessary, nothing hard. Don't make these harder than they have to be. If you can do an integral without a substitution, And it's fairly easy, do it. Okay, do that. Don't trick yourself on these problems. You're going to get 9 pi times what?
1/2 x squared. And then put down time 4/1.
So we'll be evaluating from 1 to 4. You know, I'm going to show you a slightly different way you can consider this. This is another way you can do this problem. Instead of having the 2 here with the 4 and the 1, you know that's a constant, right? You can pull out those constants before evaluation. So here, I could write this as 9 pi over 2 times x squared from 1 to 4. That's also an appropriate way to write it. So you could just look at something a little bit smaller there. You just have to not forget about the 9 pi over 2. But when you do, you're going to get 4 squared minus 1 squared. That's going to be 15. Hey.
And it works if you do it that way.
Of course it works if you do it the other way. It has to be the same. Yeah, it's going to work either way. Don't forget the pi, too. I don't want 135 over 2. Don't forget that pi. That changes things. What did we just find, by the way? Volume. That space I drew before that's being rotated around the x-axis. It'd be easy to find the area, but now we can find the volume. And how we're doing is we're saying, okay, all we're basically doing is this. Finding the height of the function at each point, revolving that height around, it's making a disk, and adding up the surface area of those disks. That's what that's doing. How many people understand this example? Now, would you like to do something a little bit cooler? This is pretty cool already. But what I want to do now, I want to see if we can come up with a formula for a sphere by doing some of this calculus stuff. You ever found out, you ever know, I mean, I'm sure there's many ways to come up with a formula for the volume of the sphere, but have you ever thought about actually how they did it? I mean, how would you do it? So take this sphere and say, well, that's got to be 4 pi r cubed over 3, obviously. I mean, clearly if you have a sphere, that's going to be the volume, right? Which is the volume, I think it is. 4 pi r cubed over 3 should give you a volume of a sphere. So how do they find that? How would you find it? Would you actually cut up a sphere and try to organize it into rectangles and add them? Probably not.
Water displacement. You
You could do that. You could definitely do water displacement as long as you know the exact value of pi, which no one does. But then come up with a rectangle that has that exact thing. It's going to be hard to do. Probably estimate it.
Yeah.
Probably estimate it. But to get it exact, wait, why don't we use some calculus and figure that thing out? Let's see if we can derive the volume of a sphere. You ready for this?
Sure.
This is good stuff. To me, the first time I saw this, I was like, dang, that's pretty cool. I thought that was really interesting. Now let's think about how you would get a sphere. What shape would you have to revolve around the x-axis in order to get a sphere?
Half circle.
Why not a full circle?
Because it'd be redundant.
It would be redundant. It would say, well, I don't need that extra part. Just a half circle would do it, wouldn't it? Take a half circle, revolve it all the way around. It's going to create a sphere. So let's start with that. I tried to do it twice and look about the same. Must be the way I'm going to do it. Okay, so we don't need this bottom part. We don't need this. But that's what it's going to create is this bottom section. When I sweep it around, it's going to create some sort of sphere. How far is this? And how far is this?
From each other?
No, I mean how far? What's the coordinate of that? The x-coordinate.
0 r.
0r would be. I'll give you the 0r is this one. That's r. How far is this one? How far is this one? Whatever the radius is, that's what it happens to be. So notice that the only the only two things you know about a circle is where the center is and how much the radius is. And we know the center is at 0, 0, at least that's what we're implying. And the radius is r, whatever r happens to be. I can't say 1, I can't say 2, because it would only be the volume for that specific sphere. I want to find the volume of any sphere for any radius, and that's what we're doing right now. So we know this is negative r to r, and this is r high, whatever that happens to be at its highest point. Whew, question. How do we find a function? See, we need to find a function, don't we? To be able to integrate this thing, we got to find a function. What's the function for half of a circle? What's the function for half a circle? Do you know the equation of a circle? What's the equation of a circle then? You're mumbling, you're guessing it. You're guessing
Yeah,
it.
it's x squared minus y squared square root.
Very good, you really do this, you'll think I know what. Say what now? X squared plus y squared was radius squared. Yeah, you kind of need to know that one. That's how you get circles. X squared plus y squared equals radius squared. Very good. Now, what variable denotes our function in terms of x here? What variable? What variable would you need to solve for to say, hey, here's a function? You'd solve for y. Yeah, very good. To say, here's a function of x, you'd solve for y. Right? R is going to be a constant for whatever type of sphere we're going to have, okay? So we're not going to be dealing with r as a variable. R is just going to be whatever radius is. So in our case, we'll solve for y. Hopefully you can see this. We're going to subtract x squared. And then what are we going to do? Now, if you square root it, you would get that. Yes, no? Tell me something about this. Which one don't we need? Yeah, actually you could take either one of them, but you don't have to have both. If you had both, it would have the whole circle. So what I'm saying is that the solid one that we have is the plus version. The dotted one we have would be the minus version. Do we need the full circle to make the sphere? No, we don't. No, we just need one of them. So take either one, the negative one or the positive one. I prefer the positive one because, well, that's easier to deal with. So we're going to go, okay, even though it has this plus minus, we'll consider this to be the upper half circle. You know what? That's about all the setup we're going to need to do. Do we have a function that has x's in it? Do we have a starting point and a stopping point? Yeah, let's set up our integral. We know the volume equals, let's do this. Where's my integral start, ladies and gentlemen?
-1.
Where's it end?
R.
Okay. What needs to go on the inside of our integral? Remember that, well, now, here's an interesting concept. Do we have planes that are perpendicular that are binding my... Yes and no? It actually stops, doesn't it?
And at that point,
So at this point,
perpendicular. You could say the tangent.
you could consider a tangent at that point, yeah. But it actually stops. It stops right there. It doesn't go, it doesn't lean in, it doesn't do anything like that. But it tangentially, yes, we have those ending points as well. So it touches that one point, it is perpendicular, so it does fit this. It means we can slice it into little bitty circles.
But it pushes the limit of it.
No, it could be angled downward as well, as long as it doesn't do this. Here's the difference. It can do this. It can do that. What it couldn't do would be this. It could do that.
It can't come back on itself, but it can, as long as it's going outward.
Yes, because you'd be missing this area, this one. Okay, that's what you'd be missing. Do you see the point there? Literally, do you see the point that you'd be missing? You'd be missing that piece. The little would get locked off because it takes it to the perpendicular. So this one, when you went down like this, is fine. You're not missing any of that.
Everything's encompassed.
It's all in there. Yeah, it's cool. You can create little slices, but this one you'd need a separate way to do that, and that would be with washers, and we'll talk about that in a little bit. That would be two different integrals. You see the point? Okay, so yeah, this one works because, yes, technically you don't have planes which incorporate your function and are perpendicular, but you do have perpendicular boundaries of your function, which is great. That's what we need. Now, okay, what's on the inside? Let's go quickly.
Our equation.
Pi, I'll give you the pi. What else do we have in there?
Parentheses.
Brackets.
Okay, bracket. I like the bracket. Why do we need the bracket? We're going to square something. We're not going to forget about it. So we're going to square it right now and have a dx on the outside of it saying, whatever's in there, whatever I'm going to put, my function has got to be squared. What's my function? Told you I'm a nice guy today. Nice guy, good numbers. So this is an integral from negative r to r of pi. Great. What happens here? Do I still need parentheses? I'm still multiplying by pi, so yes, I do. Still so far so good? Okay. What now? You could pull the pi out. Sure. If you'd like to do it. There's a couple options that you have right here on doing this integral. One of them would be to distribute that and separate your integrals into two integrals, and then pull the pi r squared out, and pull the pi out of the second integral to x squared. Or you could treat it this way. It doesn't really matter. Show of hands, how many people can make it down that far, feel all right with it? Now, here's where you got to be careful. What is the variable that we are integrating with respect to? So that means we treat r as a constant value. That means you do not do r cubed over 3. That's not the case here. X is your only variable. Are you with me on that? That's the variable. So what you do, you don't pull that out. You can't pull that out. That would mean that you'd be multiplying, right? And you're not multiplying by that x. You're not. So that's why I said you have options here. You either separate this into two integrals, which you could do, and put a big old bracket around it because you're multiplying by pi. That's one way you could do it. Or you just consider it this way. And this is the way you guys led me down, so I'll do it this way. You have the pi. You're multiplying by this integral. What's the integral of r squared? Well, think of it like a constant. If that was a 3, what you'd get over here would be 3x, wouldn't you? I hope so. Integral of 3 would be 3x. If that was a 1, you would get x. True? This is not a 3, it's not a 1, but it's a r squared. We treat that like a constant, so you're going to get r squared x. It's a constant. Integral of a constant, you just add an x to the back end of it. Think about it. What's the derivative with respect to x? R squared. So that works. That works. Remember, we're just antiderivating here. Differentiating, whatever that is. Minus, now this one, that is a function of x, it's tied to the dx, so go ahead and do that. You're going to get x cubed over 3. And we're going to evaluate from negative r to r. Now I'm going to move over here for this one. But are you okay with that so far? Yes, no, people can't hear you.
Yeah.
Okay. Are there any questions on that one so far? So you can take an integral of this, r squared x. Integral of that, super easy. Now this says plug it in. Where do I plug in my r's? To my r's or to my x's? Clearly my x's. That's my variable I'm dealing with. So quickly, we're going to have pi. We're going to have r squared times r minus r cubed over 3 minus, don't forget the minus, you got to plug in the negative r squared times negative r minus negative r cubed over 3. Are you okay on where all those things are coming from? We've got our r squared r here, and then r cubed over 3, no problem. Then subtract the whole thing, r squared negative r minus negative r cubed over 3. Now be very careful with the signs, don't lose anything, don't mess anything up. That's the real key with these definite integrals. I got negative r cubed, I got positive r cubed over 3, because that's still going to be negative, negative, negative is plus. Don't forget any brackets yet, not done. R cubed minus r cubed over 3 plus r cubed minus r cubed over 3. Two r cubed minus 2r cubed over 3. Yes, no? Common denominator would make this, well, if you multiply by 3 over 3, you're going to get 6r cubed over 3 minus 2r cubed over 3. Now that you have a common denominator, hey, check it out. What's 6r cubed over 3 minus 2r cubed over 3? Or what we know and love, volume of the sphere. Isn't that cool? I love that one. That's kind of fun. So nice and precise and interesting that we're able to find, it took us this long in calculus to be able to find the volume of a sphere. Isn't that neat? But by slicing up and using little bitty circles of a sphere. How many people understood that? Feel okay with that? Good. All right, so we've already accomplished how to find the volumes of these solids which have been rotated around an axis. We said basically that if we rotate a solid around an axis, the cross-section is going to be a circle. If we add up all those circles, in other words, disks, then we're going to get the volume of that figure. Does that make sense to you? So add up the surface area of all these disks, this infinite number of disks, you're going to get a volume out of it. The idea of volumes by washer stems from this problem. What would happen, say, if I had my famous function called f of x from A to B. Now, here's where we started. Okay, this is what we were just talking about. If you sweep this around the x-axis, it will create a volume, create a solid, and we were able to find the volume by taking slices with our disks. That's true. However, what happens if there's another function between f and the x-axis, namely, let's call it g of x. What if I swept that thing around, rotated about the x-axis? It's also going to create some sort of a solid. Do you see it? Only the solid's going to have a hole in the middle. This is actually the idea of a vase. Right? The other one, it looked like a vase, but it was a solid vase. It'd be like a vase out of concrete. You couldn't put flowers in it. This one would really be a vase. If I sweep this around, it's going to be like taking this piece and rotating it out. There's going to be a hole in the middle, kind of like a toilet paper roll, almost like that, but it's going to be a fancy shaped toilet paper roll. I mean, that'd be kind of cool, but that's what it would that's what it would be like. Let's see if I can draw it for you so you get a three-dimensional picture. This might be hard for some of you to draw. Do you get the picture, at least the idea of what I'm trying to portray here? Does it look, can you see that that's the rotation? If I rotate that out, what it makes is some outer surface, yes, and then some inner surface where the inside of that inner surface is actually hollow. Let's think about what's going on here. First thing that I want to talk about, is the cross-section still a circle?
No.
Circular in nature. Sure. Still circular in nature. If I take a cross-section, bam. But let's think about this for a second. If I think about it, well, if it's circular in nature, then this should work for us. The volume should still be some integral from A to B. Should be some integral from A to B. How we did the volume of any solid is we integrated the surface area of our cross-section. Remember that? We took the surface area of our cross-section. We integrated the surface area of our cross-section from A to B. That was basically it. So we still have this idea. Integrate from A to B. The function a of x dx, where a of x is the area of the cross-section. That seems pretty easy. Now all we got to do is find out how much is the area of the cross-section. Well, let's think about it for a second. Area of the cross-section. Well, that should be, think about the cross-section here. What's the bigger disk? Do you see the two disks that we're going to get out of this? We're getting a disk made by f of x, and inside we're getting a disk made by g of x. What's the bigger one? So what if we did this? What if we took the area of the cross-section of f of x and subtracted the area of the cross-section of g of x? Would you agree that that's going to give us the surface area of the cross-section of the piece that's actually filled in? I'll try to explain it with the picture again. The area of f of x, remember that this is f of x, this outside one? And this is g of x, this inside one. So if I take the area of the cross-section of f of x, and I take the area of the cross-section at g of x, and I subtract them, basically what I'm taking is a big disk from f of x minus a small disk from g of x, and it's going to give me the region, the difference between those circles, basically. And that's going to be the area between f of x and g of x. We're just going to understand that. You okay with it? Okay, cool. Well, so let's think about what that means then. Oh, how do you find area of a circle? Pi r squared. Pi r squared. So if area is pi r squared for a circle, can you tell me what our r is here? The r is for my f of x, my outside one. Okay, I'll give you, it's going to be y. It's going to be y at the value x, wherever x happens to be. What is y wherever x happens to be? F of x. Remember, f of x is the function, right? So how do you find out the height right at this point? Well, you just take your function, the function's value at that point. Remember, f of x says the function's height at the point x. You with me on that? So wherever I'm at, I'm given the height by just plugging in x to f of x. That will be the function f of x. So the height here is f of x. That means the radius is f of x. What's the height here? So here's basically all we said. I'm going to try to recap this for you so you understand where the formula is coming from. We take this figure that's created by f of x minus g of x. That's basically the area. We're going to sweep that area around the x-axis. It's going to create some sort of a toilet paper roll. That's the idea. A fancy one because it's not uniform in shape. It's not rectangular, but that's the idea here. So we sweep that out. We have this volume. It's solid, but it has a hole in the middle of it. What we're thinking is, if we can find the cross-sectional area, then we can integrate. If we can find the cross-sectional area, we can integrate across our, notice how we still have perpendicular sides, perpendicular to the x-axis. We needed that. Remember, for the discs, you need to be able to get actual discs. So we had to have those that work still. So this is still true. We're integrating all those discs, adding them all up, adding them up from A to B of the function a of x. That's all the surface areas of those discs. No problem whatsoever. We just got to find the surface area of the disc. The surface area of the disc, of the, well, I should say washer in this case because we're going to make that transition, of the washer is the f of x circle minus the g of x circle. That's what we're talking about here. The area of the f of x minus the area of the g of x. Well, we know areas pi r squared. Our r in any case of these cross sections is f of x or g of x respectively. So radius of our circle of our cross section, that's just the height of the function. That's right, f of x. It's just the height of the function. It just says g of x. So if we put in these areas, we should get pi r squared minus pi r squared. Hopefully you're seeing where these things are coming from. I'd love for you to understand why these formulas actually work. What are we really doing? What's this stand for? No, this whole thing.
Oh, the area for the first function.
Good. Whatever the outside one is, the top, we'll say the top one in this case. The top one, that's the radius. The height of the function is the radius. Square it, times it by pi, you get an area. This is the
Inside.
second, inside, whatever you want to call it. The g of x in this case. Radius, square it, times pi, that's the area. Area of the large disk minus area of the small disk gives us the area of a washer, the surface area of a washer. If we want to be a little bit fancier about this, we'll probably just factor out the pi. Just factor the pi out. And then what that says is we actually have the expression for a of x that we're looking for. We're going to do the volume is an integral from a to b, sure. Pi is going to be there. We're just going to integrate the surface area of a washer from a to b. That right there is called the volume by washers. That's what we just found. Would you like to do an example? Okay, I was hoping so. Otherwise the lesson would stall out and be like, okay, so what do we do now? Party time. No, not so much. Okay, that's very wordy, but I wanted to make sure you understand exactly what we're doing. This is what we're doing. We're trying to find the volume of the solid that's created when the area between two functions, f of x and g of x in this case, between the interval, on the interval 0 to 2, is rotated around the x-axis. That's the whole idea. Now, we should be able to set this thing up and find the volume of that.
You're subtracting the two functions, so is it possible that you can compose them? Like, can you, like, f of, then you mean like f of x minus, like plug g of x into that.
It's not a composition, no.
You can't do that.
Sure, you might be able to, but it's not going to give us the volume that we're looking for. Okay, now, what's important for us to know before we start this problem?
On top.
Say it again.
Which one's on top?
Why would that be important?
Because it knows if the order's
Yeah.
patching.
If you subtract them incorrectly, you are not going to get the right answer. You're going to get some sort of negative volume. Can things have a negative volume?
No.
That's crazy to think about, but no. You can't have a negative volume. Well, maybe the opposite of complete, vacuum, I suppose. But that's not even,
Black hole.
still has something. In fact, it has a lot of mass, actually. The center of a black hole. So, no, we can't have negative volume. What we could have is positive volume, but we need to make sure we set it up right in order to get positive volume. So it says you need to find the one on the top, you need to find the one on the bottom. That way when you do subtract them, as Sarah said correctly, when you subtract them correctly, you get the right answer. We need to know which one of these is our f of x and which one is our g of x. That way you set our problem right. So how would you do that?
So you can do yourself.
Not quite, because I'm already giving you the interval. You're making it harder than it is. If you set them equal to each other, you're going to... If you set them equal to each other, you're going to find the places where they intersect. If they do intersect. These don't intersect. I don't think they intersect. Someone do the math real quick in your head. I believe they don't. But x squared plus 1/2, that goes like this. X goes like this. They're not going to intersect. Okay, so even if you set them equal to each other, you get x squared. Oh, maybe they do. Minus x. Don't know. I don't really care. But no, that's not the way you
Yeah,
do they really?
because you have one F right there, and X is going to
Let's see. I gotta see. I gotta see. No, they do not intersect. Discriminant tells us that. You get b squared minus 4ac, that's negative, true? So b squared minus 4ac is negative, that means you do not have a solution for a quadratic formula, which means these things cannot intersect in real numbers. Therefore, no, these don't intersect. Shame on you people for saying yes, they do. Not shame on you, it doesn't really matter. But no, they don't intersect, but that's what that would be doing for you. So if you set them equal to each other, you're going about it the wrong way. That's too much work for this problem. Again, you'd be making it harder than it needs to be. This is not hard to set this thing up. All you need to do is figure out what's on top for the given interval. How do you figure what's on top for the, I gave you the interval. If I didn't give you the interval, that's when you would set them equal. That's when you solve to see where they intersect. You get me on that? So what do you do here? Plug in a number. Yeah, one's always going to be on the top of another one. That you might check by, let's see if they do intersect. Send them equal to each other. Do they cross over? That's what that would do for that interval. Here, I'm just telling you, I told you already, this one is going to be one function, this one's going to be another one. One's already going to be on top of the other for the entire segment. So between 0 and 2, one's on top. Otherwise, I would have worded it a little bit differently. So if one's always on the top, plug in a number. What number are you going to plug in? 1. I would pick something in the middle of it. 1. Doesn't really matter. But plug in 1. If you plug in 1 here, you're going to get 1.5. If you plug in 1 here, you're going to get, which one's higher? So this is going to be higher than this one, right? It's always on the top. I drew the picture for you, but that allows you to set up even without a picture. Can you tell me where we start on this? Where do we end? What are we going to have in here? Good, pi. Then a big old bracket, because we're going to have a couple functions being squared in there. And that pi, we can even pull that out of our integral if you'd like to. It's a constant. It can do that. What goes on the inside first? Tell me first. Okay, good. What are you going to do with that function? Then what are you going to do? Subtract what now? Now I'm going to put it in a bracket just so you see that this is the second function. So notation-wise, I want to be consistent. Let's see if we can get it. We've got our formula here, which says you have the pi, no problem. That's going to give us the, well, that's basically our formula from area to circle. We have the outer disk minus the inner disk, but we got to square them because they're the radius squared. How many people feel okay setting that problem up? Did you feel comfortable this side? Do you guys feel all right with that? Do you feel comfortable getting that this one was on the top of our g of x? This one's first, this one's second. Now what? Probably. Go for it. See if you can FOIL that out. So foiling all that out, if you do in your head, great. If you want to write off the side, great. Just get the right answer. Make sure you FOIL it correctly. This is going to be 1/4 plus x squared plus x to the 4th, and then you have this minus x squared. I would like to know if you got the same thing on your paper that I got on my paper. Did you get the same thing? Yes? No? Good. Oh, okay, good. What happens here?
We have to cancel each other out.
Which is kind of nice. You see, the thing about it, you could do this two different ways if you really thought about it. You could find out the volume of f of x and find the volume of g of x and just subtract them, couldn't you? Which, that's another way to derive this formula, by the way. It's the same exact thing. You'd have the same balance, right? Put them together. It'd be subtracting integrals between the same bounds with a common pi. You'd factor the pi. Same thing. You could do it. However, you're creating more work because when you do an integral of f of x, or the area of f of x, and do the integral of the area of g of x, you're doing two different integrals and doing all the bounds, when sometimes you get this situation where you can combine like terms. Sometimes things go away, so it's nice to do this rather than two separate integrals. Do one larger integral. You seeing the point on that? That's why I give it to you this way. So x squared's gone. Love that. What do you say we pull that pi out? We got 0 to 2, 1/4 plus x to the 4th dx. The pi is going to stay there. Can you take your integral of 1/4 plus x to the 4th? What are we going to get? Say what now?
4x and 4.
Okay, x over 4, that's great. 1/4 x, doesn't really matter. It does need to be in parentheses though. It has to have a bracket. Plus what? And we'll be evaluating that from 0 to 2. So I'll have my pi out there. I'm going to do 2 over 4. Plus 2 to the 5th over 5. And then I'll subtract, but when you plug in 0, you're going to get 0. So I'm just going to show it this way, just to make sure I don't have anything wacky going on with that 0. Make sure I have it up there. That's going to be our volume when we multiply by pi. So 1/2 plus 32 over 5. How much?
69/10.
Okay. I think your calculator will do that for you, but 69 pi, don't forget the pi, 69 pi over 10. What did we just find? It's kind of cool. We actually find the volume of some solid, whatever it was, as long as you know the function on the top and the bottom, some solid revolved around the x-axis. That we found out how much, if you were going to pour this out of concrete, how much concrete you need. 69 pi over 10 yards or feet or whatever, cubic feet, I suppose.
Contractors place that order.
Right. Yes, hello, I need 69 pi over 10 yards of concrete. Yeah. Oh? Unless you know calculus, you're like, you got it, son. I got that.
Yeah.
You got it. See? See? Even contractors might know how to do that.
Maybe the greatest concrete contractor ever.
How many people understood this example feel okay about it? Now, can you do this when we revolve around the y? We've been going around the x the whole time. Can you do it this way?
Probably.
Well, I hope so. The ideas aren't going to change. It just says what happens if you have a figure going up and down rather than left and right. The formulas will be very similar. The only difference will be, well, of course, the variables will be slightly different.
Yeah, you can really accept that.
So let's talk about volumes that are perpendicular where the planes of the interval are perpendicular to the y-axis. So volumes where the cross-section is perpendicular to the y-axis. Before we had the cross-section perpendicular to the x-axis. That's why we were able to take and make all those little discs out of it. Here we got this way. Well, if we talk about it, the discs method then would end up looking like this. Instead of from A to B, we usually use from C to D for the y-axis. So we go from C to D. We'd have some area function, but the area function is still going to be a circle. Pi r squared dy. Where u of y would be your function in terms of y, not in terms of x. Where u of y would be your function in terms of y, hence the y, instead of x. That's the idea for the discs. For the washers, very, very similar. Still from C to D. Still a pi. Still the radius squared, some outside function, minus some inside function, squared. Hopefully it looks familiar to you. It's basically the same exact idea, only you're going to the y-axis instead of the x. I'd like to give you an example if you don't mind on this. Would you like to see one?
Sure.
Now the process won't be any different, it really won't. Just have different variables. But this stems from this idea. What if you were to take... By the way, I only know how to draw one function like this, so that's why I do the same one over and over. I took it and went that way, basically. If this is u of y, then the solid would look like this. Well, it's not in proportion, but hopefully you get the idea. We're just going this way with it. Taking this solid, rotating it around the y-axis, we'll get that sort of shape. Notice how we're perpendicular to the y. All the cross sections will be perpendicular to the y. That means we can integrate from, instead of A to B, we usually call it, again, C to D. We can still integrate from C to D. Add up all those cross sections basically. Let's try it. I'd like to give you several examples on this. So I don't know if we'll finish this today, but I do want you to see a lot of them so you get kind of a handle on it. So we'll start kind of nice and easy, work our way up from there. So let's say this. Y equals the square root of x is revolved around the y-axis. And it's bound by y equals 2 and y equals 0. what I'd like us to do is find the volume. Now, you can draw a picture of this, but you don't need to. I want to draw the picture so you see what's going on, but you don't need to draw the picture. You just need to understand what all these pieces mean, okay? Here's the idea. There's x squared. You with me? Now, bound between y equals 0 and y equals 2. What is y equals 0 and what is y equals 2?
Horizontal line.
They are. Yeah, in this context, they're horizontal lines. Remember, y equals a constant equals a horizontal line, yeah? So what this says is, when you go up to 2, it's bound by this. And it's bound by this. This is y equals 2 and y equals 0. So essentially, I'm not worrying about this piece of the graph. I'm just worried about this piece. Now here's the problem. Am I going this way or this way? It says around the y, so I'm basically taking this shape and making this out of it. Making that shape out of it. Do you think the volume will be different if I go this way versus this way? That's an interesting question. Why don't you figure that out later, see if it is. Right now, that's not our question. The question is, can you take this, go this way, and find, between those, basically, lines, and find the volume of it? Question.
When we're taking it with respect to y, if we want to figure out if the volume is the same and we turn it with respect to x, will our bounds change as well?
If you turn this way,
Yeah.
I don't even have any bounds.
You said bound by 2, y equals 2 and y equals 0.
Right.
So if you did it with respect this way, about half of it.
But, okay, I see what you're saying. So like that right there?
Yeah.
Okay. Yeah, you could do that, but I'm not asking with respect to x. I'll give you the long story short. No, the volumes are not going to be the same. One's going to be completely different than the other one. If you take this and roll off this way, or this way, you're going to have different volumes, significantly different volumes. Okay, it's not going to work the exact same way. Could you do it revolved around x? Yes, but that's not what I'm asking for. I'm asking for, can you revolve it around the y? It'll give you a completely different looking shape even. This, if you revolve it this way, is going to give you kind of like a bullet point, right? This gives you some sort of a weird looking cone thing. That's a technical term for it, at least. Weird looking cone thing. So you have this shape, almost like a flower coming out at you. That's what that's going to be. Now here's the issue. I'll give you a little note as well. When you're revolving things around the y-axis, you need to have them in terms of y, which means you need to solve for x. Don't let that confuse you. I'll say it one more time. When you're revolving around the y-axis, it's got to be x equals y. Does that make sense? When you're revolving around the x-axis, you had y equaled something in terms of x. That's what we did. Oh, I erased the problem, but that's what we did over here. You had all x's, didn't you? F of x, g of x, they're in terms of x. That's because we're going around the x-axis and our bounds are in terms of x. What are our bounds in terms of here? Y, that you better have y's to work with then. So the note for you, when revolving around the x-axis, functions must be in terms of x. That means solved for y. When revolving around the x-axis, put functions in terms of x, because your bounds are in terms of x. You have planes that are perpendicular to the x. It's all about the x. Solve for y. When revolving around the y-axis, it's backwards. Put everything in terms of y. Your functions needs to be in terms of y. Your bounds are in terms of y. Your planes are perpendicular to the y. It's got to be in terms of y. Solve for x. That's the idea. Notice that if we're revolving around the y, you're using this thing, you really are. You're going from C to D, u of y. That's why I put u of y over here, guys, so that you'd see it has to be in terms of y, not x. You're going around the y-axis, it's got to be in terms of y, dy. So for us, let's see about our function. If y equals the square root of x, is this in the right form to go around the y-axis?
No.
This would be around the x-axis, perfect. Oh my gosh, it'd be awesome for the x-axis. In fact, if you want to right now, you could probably figure, well, you'd have to do a little bit of work for bounds, because your bounds would change. Do a little bit of work for that, you'd have the square root of 2, kind of awful. No, you'd have 4, that wouldn't be so bad. So you could do that and figure out that the volumes are not the same. But that's not good enough for going around the y. How do you make it go around the y?
Get x equals y squared.
Get x equals, very good. And you get that by squaring both sides? Sure, we're going to get, if you square both sides, x equals y squared. What's the function that we're talking about, x or y squared? Look what this does. This says, no, 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 I don't want the square root of x anymore. We'll consider it y squared from here to here. Just that little piece though, just that little piece. So we'll have, let's see if we can do our integral. Where are we starting, ladies and gentlemen?
0.
Somebody else, where are we ending? What function goes on the inside? Oh, you know what, I forgot a couple key parts. Of course we want to fill that out, right? I get so excited just doing this. Forgot this. We do mean this, of course. We got to have a pi. What else are we going to have in there? What do I put in for my function? What's my function? And then what?
Squared.
Mm-hmm. So these are in terms of y. Y equals 0, y equals 2. That's not a problem. We put this one in terms of y. That's our y squared. We fill out our formula that we got. Now, why do we have discs and not a washer? Yeah, we only have one function. There's nothing between them. So we can use the disk method just fine. There's not another function to take away volume from it. Can you do that integral? Yeah, that's actually pretty basic. Let's go ahead and do that. We'll get pi from 0 to 2, y to the 4th dy. That's pi. Y to the 5th over 5, because we know how to do integrals real well. From 0 to 2, pi will do 2 to the 5th over 5 minus 0. What we're going to end up getting is 32 pi over 5. By show of hands, how many people feel okay with that so far? Would you like to see if the volume is the same go another way? If you want to, it's not hard. I mean, why don't you try it on your own? Well, that'd be a good practice for you right now. Set up if I switch this to going around the x.
And leaving the bounds the same?
Nope.
Okay.
Got to figure out the balance.
Let's do it that way.
Don't just give up on it. Come on. Try something. Try something. This part should be pretty easy, right? If we're going around the x-axis, we got the pi, we got the r, that's our function, square root of x, and we got the square. Raise your hand if you set up just like that. That way. Yes, guys over here too? Okay. The problem is our bounds. How do we find our bounds out? If we have y's right now, how do you figure out?
Plug them in.
Plug them into X.
Plug them into x. What are you plugging them into? If y equals the square root of x, and you know y is 2 and y is 0, can you figure out x's? Doesn't this look similar to a u substitution when you're changing bounds? Yeah. Very similar idea. So this says plug in 2 for y. 2 equals square root of x. 0 equals square root of x. Square both sides, x equals 4, and x equals 0. You follow me on that? So now we'll have an integral from 0 to 4. It's going to be a pretty easy integral. It's going to be pi 0 to 4 of x dx. Square root of x squared is x. That's kind of awesome. That's great. Then we'll have pi x squared over 2 from 0 to 4. Pi 4 squared over 2 minus 0 equals same? Way different. Yeah, quite a bit different. Actually, not quite a bit different. I guess it's off by just 1/32. But anyway, one pi.
Calculus, that's huge.
Pi over 32. It's off by pi over 32. Huge difference. Huge. But it is different, not the same. So now that you see that, I am satisfied. How many people understood both these examples? Is the calculus hard?
No.
Not really. You know integrals, right? You know them. And I have to give you nice ones to be able to do them. So they're nice. Just remembering how to do it, how to set it up, and being prepared. Don't worry, we have time still. Being prepared that you need to know what variable you have to have the function in terms of, all right? I got to forewarn you here. In the next section, I'm going to give you a different way to find volumes. It's going to be volumes by cylindrical shells. And in that case, your variables kind of switch. If you're going around the y, you want in terms of x. If you're going around the x, you want in terms of y. That switches. So be careful on these these methods. If you're doing discs and washers, your axes match up. Around the x-axis in terms of x. Around the y-axis in terms of y. For the next method, it will switch around the y in terms of x, around the x in terms of y. So get really comfortable with this, that we don't forget about it. You got me? Now we'll stop there today. We'll talk about a few more examples next time. All right, so we're in the practice stage of whatever section we're on, 5.2 I believe. We're in the practice stage and just doing some examples. So the questions are normally worded something like this. Find the volume of the solid that's contained between a couple lines. They'll give you boundaries or not, contained between these two functions, and revolved around, they got to tell you which axis we're going about. So basically this says, find the area that's between there and revolve it around the x-axis. That's going to make some sort of a solid that's going to have some sort of a volume. You with me on that? Now, just as a refresher, if we are revolving around the x-axis, note that your equations should be solved for y. They should be x in terms of x. So y equals and then a whole bunch of x's. That's what solved for y or in terms of x mean. So around the x must be dealing with x's. You got it? Around the y must be dealing with y's. So my question is, if we're going around the x, are these okay?
Yeah.
Absolutely okay. Yes, we're going around the x. They are in terms of x. In terms of x means solve for y. And these are solved for y. So this is in terms of x and in terms of x, which says this, all the terms have x's in terms of x. The terms are based on x. You get it? So those are perfect for us. Now, the problem is, do I give you any bounds right here? Do you know which one's on the top right now? Do you know which one's on the bottom right now? So those are things we're probably going to need to figure out in order for us to set up our integral. Remember that the volume is, I think I gave this to you last time, a to b pi f of x squared minus g of x squared dx. Did I not give that to you? But this implied that f of x was the top function. g of x was the bottom function, so we need to find those things out. We also need to know, well, it says the volume in which the area contained by, we need to know where to start and stop. So where the area starts and stops, according to the y or the x in this case. Because we do it with x's, that's right, according to the x-axis. Nod your head if you're okay with the idea of this so far. So how do we find out, this goes back to our area problem, very similar idea. How do we find out where these things are contained, where the area is contained? Say it again? That's exactly what we would do to find the area between two curves, right? Well, hey, all we're doing now is finding the area between, look at that, the area between two curves, and then taking the circles when we rotate them around. That's all we're doing here. So this really says take the area between the two curves and revolve it around. That's what we're doing. So what we need to do first is exactly what you said. Let's set these things equal to each other, figure out which one's on the top. So what we want to find is the intercepts. Where they intersect, where they intersect. By they, I mean the functions. And also which one is on the top. Okay, so let's find out where they do intersect. If we set them equal to each other, this is kind of nice because it's already solved for y. Basically, we have y equals x squared and y equals x cubed. Setting them equal to each other gives us x cubed equals x squared. Still okay with that so far? Solving that, well, we get what? What would you do to solve that? Probably because you're going to be using some sort of factor. X cubed minus x squared equals 0. Now what? If x squared times x minus 1 equals 0, can you solve for my x's, please?
0, 1.
Perfect. Not so bad. In fact, it's very similar to what you did for finding the area because that's exactly the same idea that we're doing, only we're revolving around some sort of an axis. Now do you know where your integral is going to start and stop? That's pretty great. So we can already start filling this thing out. The volume is going to be from 0 to 1. Not a problem. That's where these functions intersect. Therefore, the area must be contained between those two things. Okay, they got to be between there somewhere. Now, what we need to do is find out which of these functions is on the top for that interval and which of these functions is on the bottom for that interval. How do you do that? Remember doing this? Remember doing that? I gave you the graphic organizer. I said, plug a number in there. Plug it into x cubed and x squared in this case. Figure out which one's on the top and which one's on the bottom. What number are you going to plug in between 0 and 1? 1/2 would be great, 0.5, whatever. With something between there, it doesn't really matter as long as it's not 0 or 1. So plug in 1/2 to both of them. This gives you 1/8. This gives you 1/4. Which one's on top? X squared is a bigger number than, I'm sorry, 1/4 is a bigger number than 1/8. Therefore, x squared is on the top, x cubed is on the bottom. Is this coming back to you at all? Do you feel okay with our setup thus far? Well, we already know where we're starting, where we're stopping. Let's go ahead and figure out the rest of this thing, the rest of our integral. We already know what our f of x is going to be in this case, the top function, and the bottom function is going to be in this case. So let's continue. What's the next thing I should write here, ladies and gentlemen? Yeah, they're all going to have a pi. That's from the circular nature of revolving around an axis. Then we'll have a big parentheses. What goes next? Just x squared? Now you don't have to use brackets, you can use parentheses as well. Just make sure you have the right idea. We take the top function, we square, that's what it says. Take the top function, square it. We have that. Take the bottom function, square it. We have that. Top, bottom. Now we're set, we're ready to go. Raise your hand, feel okay with doing all this so far? Not bad. Do you see how similar it is to finding the area? Very, very similar. Can you do the integral? Sure. What are you going to do first?
Simplify.
Probably pull the pi out. Square this, you're going to get x to the 4th. Square this, you're going to get x to the... Perfect. Perfect. Now when we do the integral, remember to actually do the integral. What this means, notice how I'm writing these things. I've seen some notation problems in some of your work. Notice that when I do the integral, firstly, I actually do it. I do x to the 4th, and I don't plug in numbers to x to the 4th. I first need to go x to the 5th over 5, of course. Also notice that when I do the integral, I've stopped writing the integration. I have the bracket, sure, but I've stopped writing the integral. That's not appropriate. If you take an integral, you stop writing the integral. Minus x to the 7th over 7. And this is how you show you're going to evaluate. Off to the right-hand side between 0 and 1. Also, there's a few people who have forgotten that sometimes 0 is a number you have to plug in and is not going to give you 0. In this case, if you plug in 0, yes, you're getting 0, no problem. But if I had like an x minus 1, and you plug in 0, that's not going to give you 0, so be very careful on that. So let's go ahead and do the rest of this. If we do pi, plug in 1 here and 1 there, you're going to get 1/5 minus 1/7. And just to make sure I'm not forgetting anything, I'm going to check to plug in 0. 0 over 5, I know that's 0. 0 over 7, I know that's 0. So I'm going to write the 0 just to show that I've done it, that I haven't forgotten about it. You don't want to forget about that thing. So basically we have 1/5 minus 1/7. Do 1/5 minus 1/7 for me, please. 2/35. Or in other words,
I think, isn't it 12?
12/35?
Oh, wait, no, yeah, because,
It's minus 5.
Should be 7/35 minus 5/35 should give you
Oh, yeah,
2/35. It's all good. You guys able to get 2/35? 2 pi over 35? Don't forget the pi. I mean, that's important, right? Don't want to leave that hanging. That's going to really change the answer. Any questions on that one before we go to the next one? Remember, this is practice. You know how to do all this stuff at this point. We're just kind of practicing, get a real good feel for it. Are you ready for another one, or do you have any questions? Okay, let's switch something up a bit. Talk about a different type of problem. Maybe not around the x-axis. Maybe we go around the y-axis. So the same idea. I'm not going to write the whole thing out. Area contained by y equals x squared, x equals y squared. That should be fun. Around y-axis. Now, could you please tell me something? Would you please tell me that if I'm revolving around the y-axis, what must my functions be in terms of? So solved for x. Solved for x means in terms of y. Means your terms are y's. That would be solved for x. So in our case, which one is okay for revolving around the y-axis? Is this one okay for revolving around the y? Is this one? That's perfect. This is what we want for revolving around the y. For the method of discs and washers, that's what we want. This one, not so much. If we're revolving around the y, change it. How are you going to change it?
X equals the square root of y.
Very good. Now, I think we're neglecting something here. Really, when you take a square root, you should have a plus and minus, right? However, this function is only going to intersect the positive version of that. If you think about that, you have, well, I could draw it, I suppose. Y equals x squared. You have x equals y squared. That's the only intersection that's happening. So we're going to neglect the negative version of that, x equals y squared, just because it wouldn't intersect anyway. Do you follow me on that? And you could show it by actually setting it equal, but you're not going to get a real solution out of it. It's not going to happen. Or you get some false solution. So are you okay solving for x in this case? Take a square root, plus and minus, yes, but the positive or the negative really isn't going to affect us in any way, shape, or form, so we're going to ignore it for us. Now, what do we need to know after that? To set, remember, our whole goal is to try to set this thing up.
What's on top?
Well, we need our balance.
We need the balance. Remember in terms of y, so everything's got to be in terms of y, nice and neat. Someone said bounds. How do you find bounds? Now, check it out. Do you see why you need this in terms of y? If I set the functions in terms of y equal to each other, I will be solving for y's, right? And this is around the y-axis. It would be useless to solve for x's if I'm going around the y-axis. That wouldn't make any sense. That's why I have in terms of y. All right, well, set them equal to each other. I know x equals square root of y. I know x equals y squared. Therefore, if x equals the square root of y and x equals y squared, that means square root of y equals y squared. So far, so good? Solve for y. How would you do that? Hmm?
Get it to one side.
Not yet.
Well, you know, by looking at it, that
Without just by looking at it.
Change the square root.
How?
Both sides.
Square both sides might be the best way to go. How do you get rid of a square root? Square it. Not square root of square root, but square it. If I square both sides, it's legal to do. You can do pretty much darn near anything you want to an equation. Almost anything you want to an equation, as long as you do both sides. Which means that even Joe, if you had changed it to a 1/2 power, to get rid of the 1/2, you'd still multiply it by 2, correct? That would be essentially the same exact thing as squaring it. So square both sides. Notice you're going to get y equals... Now say what you said, Alan. What do you do next?
You bring them to one side.
There you go. 0 equals y to the 4th minus y. Now what would you do?
Factor.
Sure. We can factor as much as needed. Here, y equals y cubed minus 1. Now, when you do this problem, you're going to get y equals 0 and y cubed minus 1 equals 0. Can you solve for y? Yes. Yes, you can. Add 1 and take a cube root, and you're going to get still 1. The only way this is working is if y equals 1. That's the only way that happens with a cube. Not negative 1 because it's not a square. It's a cube. So the only way you're getting 1 from cubing a number is with positive 1. Negative 1 cubed is negative 1. That's the only thing that would work. If you want to show it explicitly, you'd have y equals the cube root of 1, and that is 1. By a show of hands, how many people feel okay getting that far? Yes? Yeah? It is just an algebra, but it's kind of nice to review that so you don't get stuck on the algebra when you're trying to do calculus. That's the biggest problem with calculus. Hey, do we know where our integral starts and stops? Where?
0, 0, 1.
Along the y or the x?
Y.
Very good, because this is in terms of y. We solve for y. So already we know that v equals 0 to 1 in terms of y. Now, the idea of which one's on top changes when I'm talking about the y. On top doesn't mean this way anymore. On top means this way right now. Do you get that? So really we're asking which one is on the right and which one is on the left. You still do it the same way though. You still, I mean, basically, you don't even have to draw a picture or think of it. You just have to plug in a number and figure out which one's bigger, that goes first. Which one's smaller, that goes second. That still works. Only bigger this time means right, smaller means left, and then you'll be revolving that. Nod your head if you're okay with that. I know we're talking lots of theory here, and not lots of theory, but it's abstract because I can't draw a lot of this stuff very well. So how do you do it? Same thing we just did here. Same thing. 0 and 1. We'll take a number and we're going to plug it into right here. What number are we thinking about? You could do 0.5. I might do 1/4 because I can take a square root of it very easily. And I'm going to have to take a square root. Do you understand? Maybe take 1/4. So if I plug in 1/4, just do it to both. This gives you a half. This gives you 1/16. And we can clearly see which one is bigger and which one is smaller by using some numbers that we actually understand. So which one is the bigger one? So then square root of y goes on the top. Nice graphic organizer, huh? Tells you which one exactly goes where. Which one is on the bottom?
1/2.
Now, of course, bottom means left, top means right, but you set it up the same way. So which one, in other words, is going to come first? The square root of y or y squared? Okay, fill out the integral for me. So what am I going to have?
So the square root of y squared.
Pi. Okay, can't forget the pi. Square root of y, I heard squared, very good. And then, yeah, don't make the mistake of putting a plus, right? We're actually subtracting volumes here. Subtracting, surface area and then revolving that. So I'll make that bracket. What's the next one? I heard you. I'm going to write it this way. Feel comfortable setting up the integral? Notice really the setup and the plugging in numbers is the hard part here. That's the hard part. The integrals, most of them are going to be very doable for you because otherwise we get stuck. You know, maybe I'll pull that pi out of here. We got a constant anyway, we may as well pull that out. Square root of y squared, that's kind of nice. I just get y. Minus, this is going to give you y to the 4th dy. Not such a bad integral to do after all. We get a pi. We're going to get y squared over 2 minus y to the 5th over 5. And we're evaluating from 0 to 1. Let's plug in the 1 first. That's what it says to do. So we're going to do 1 squared over 2. That's just 1/2. Minus 1 to the 5th over 5. That's just 1/5. I'll check the 0, but I know I'm getting 0 minus 0. That's still 0. 1/2 minus 1/5 should be 3/10. Bam. Not too bad. Not too bad. As long as you understand the idea here that find out where they actually intersect. Set up the integral appropriately. Make sure you can find out which one comes first and which one comes second. And then it's all about the formula work. Just plugging it in. By a show of hands, how many people feel okay with what we've talked about so far? Now I'm going to give you one more. I would consider this to be kind of a tougher problem. But it's going to take us a little while for me to explain it to you. But I want you to see it. I don't think I've given you any homework on it. I might have. I don't think that I have. I don't think I changed the assignment. But I will certainly give you something to do with this. So see if you can comprehend the idea here. What if I ask you to find the volume of the solid contained by this and that is revolved around y equals 3/2. That's an interesting question. It says, right now we're not going around an axis. Right now it says, imagine this. You have some sort of an area, right? Instead of revolving around a y-axis or an x-axis, you're saying, pick some line, revolve around that. Can you still do it? The answer is, yeah, we can, as long as you understand what the concept is that we're doing here. Now, I'm going to draw the picture of what this is. You don't necessarily need the picture to do it. You can do it the way I showed you, as long as you understand what's going on. So I'm going to illustrate it so you do understand the way it's going on. First thing I want you to get a picture of is what's taking place. Now that's a pretty easy function. That just says y equals x, yeah? And this one says y equals x cubed, which looks essentially like this for this interval. And if you really want to find out where they intersect, where could you do it? Or how could you do it? Okay, so if I set them equal, I would get x equals x cubed. I would get 0 equals x cubed minus x. I would get 0 equals x squared minus 1. For the sake of keeping it easy, I'm just going to focus on the positive here. We're going to get 0, 1, and negative 1. I'm going to, just so you make a note of this, I'm going to ignore this one to keep it easy for us. Also, you can think back to odd and even functions. If I were to revolve, oh no, that's not true because we're revolving around something that's not x-axis. Disregard that statement. To keep it easy, I'm going to keep between 0 and 1, just so we make it easy on ourselves. You can do it another, you could also do this with the negative portion of this, but it would be a different integral. You'd have to do 2 different ones.
Now that won't leave out any of the volume or area.
Of course it will. If I remember that this would also do this, right? I'm saying, let's, just to find out what this is going to be, let's forget about this for a second.
Okay.
Because you'd have to do a different integral anyway. You'd have to set up a completely different integral anyway. Because they cross over. One's not on top of the other one the whole way. So you have to do it a different one anyway. Let's just focus on this one for right now and see how to do the problem in the first place. Do you understand what I'm trying to do here? So all I'm really saying is this is 0 and this is 1. That's what I'm saying. Now, so we see the area. What are we going around? This? This? Are we going around this? No. What is y equal 3 halves? What's that? Is it a, oh come on, you should know.
Horizontal line.
Is it this way or this way? It's this way. Y equals 3, y equals a constant, just gives you a horizontal line. Y equals 5 would be at 5. Y equals 2 would be at 2. Y equals 3 over 2 would be at 1.5. So if this is 1, which it is, 1, 1, what we're talking about is, can you revolve this figure around that, treating that like the axis? Now that's a really interesting question, isn't it? It's kind of crazy. Can you do it? Well, we're going to think through it as to how in the world we might do this, and it's going to stem from this formula, but we're going to change it just a little bit. By the way, with questions on that? Yeah. I asked you that, Bill, already, I think. Oh yeah, this way. So we're revolving around that one. Now let's think of what actually is going on here. What does this represent in our formula? The top, sure. But what is this? Well, let me. I'll kind of split it apart for you again. A to b pi f of x squared, minus g of x squared dx. Before I go any further, I better make this clear also. What should our variables be in terms of x's or y's? X's, because we're really going this way around that. It's almost like an x-axis that's been moved up a little bit. Do you get why we're in terms of x and not y? If it was this way, yes, y. Basically it goes where are the planes perpendicular to that you're going to find the area of, and then consequently the volume. They're perpendicular to the x-axis still, so they have to be this way in terms of x. Well, what does it mean when I do this? What are those things? What do those look like?
Circles.
They're circles. So what is f of x? Say it again.
Radius.
It's a radius. What is g of x? A radius. Now, that worked very well because f of x can be considered a radius if you're going from the x-axis, can't it? This would be the radius of that figure being rolled, and this would be the radius. However, I'm not going around this. Now I'm going around this. So if we can find out the area of those cross sections, remember doing the cross sections by washers, if we can find out the area of those cross sections, incorporating this y equals 3/2, we should be able to do a very similar thing. So let's think about it. If I'm to revolve, so this is, f of x is basically a radius. If I'm going to revolve this thing around the 3/2, can you tell me what the rate, it's going to be so hard for me to draw, I don't know if I can do it. I'll try. It's hurting my head.
Too many circular shapes.
There's so many going on, but it almost looks like an eyeball, looks like an eyeball, but that's flat. This is flat at the end, this is flat at the end, and there's this little space that goes around. Do you see the space that goes around? That, oh, you know what, this would make it a little clearer, this right here. There. We have that space that's going around that. What we want to figure out
It's
is,
like a sideways bulb.
kind of like that, yeah, very much, with the open bottom and open top. If this is y equals 3/2, here was basically the idea for going around an axis. Look, find the radius, square it, times it by pi. Find the other radius, the inside radius, square it, times it by pi, and then subtract them. That's the surface area of the outside one, minus the surface area of the inside one, and then we integrate the surface area. That was the idea. Did you get the idea? Well, now this is very similar. Let's just think the outside one is, or what the inside one is. When you go back to here, what function is this stemming from? Look at the function. X cubed. What function is this one stemming from? Okay. Would you agree that the outside function is x cubed?
Yes.
And the inside function is x?
Yes.
Let's find a radius that's based on 3/2. How would I find out the distance? Oh, let's think for a second. At any random point x, okay? How would I find the distance between a constant line 3/2, let's say right here, 3/2, and this is what I'm looking for. How far is that? Say it again.
3/2 minus x cubed.
It'd have to start with 3/2, wouldn't it? Because 3/2 is a little bit higher. Have to start with the 3/2, because that's here, 3/2, and then you said minus what?
X cubed.
Ah. Would you agree that at any point the height of this function is x cubed? Therefore, at any point, the distance between here and here is 3/2 are constant minus x cubed. And that's exactly right. Can you do the same thing for a random point from here to here? How much is that?
3.5.
3 halves, that's where we start, that's our constant, minus x. That's the height of the function at x. So right here says, this whole thing from here to the x-axis is 3 halves. The thing from here to here is x. So if I take 3 halves minus x, I will find the radius. Now that's kind of hard for some people to grasp. Do you grasp it? How many people do feel okay with that?
Now, is that for the entire thing, like if you were to do above 3?
Radius is the radius, right?
Yeah.
So we use the fact that this is apart from the x-axis to figure out the radius. Whether or not this is above or below, that's the same distance. It's still 3 halves minus x. Did you get that?
That's right.
You sure? So radius is radius. Doesn't matter how you get it, that's the radius. Now, we're going to go ahead and fill this out actually, using this idea. This was the radius, that's why I walked you through this. This was the radius, this is the radius, correct? So for us, when we have a y equals a constant line and we're going around that actual axis, it's going to augment this just a little bit. It says, well, really what we have is the y equals a constant minus the, in this case, it's the outside function, not the top function, the outside function. I know it's weird to think about. Outside function. Inside function. Outside, inside. Now, I don't know if they give you that form in the book or not. I don't think that they actually do. But they expect you to understand the idea that all you're doing is taking a sliver of it, a slice, a washer, finding out the radius, look at that, the radius here and the radius here, squaring them, times them by pi, and then subtracting them. You find the surface area of the outside circle minus the surface area of the inside circle. In this specific case,
Why does moving its point of revolution change the area of the actual area? Wouldn't the area still be the same whether it's on the x-axis, it's just location
no,
and space?
think about how much further away you are. This is actually touching the x-axis, right?
Okay.
And you're just going right around it. This is sweeping out. Think about if you're this far away, you're this far away out here too.
Right, but the inside part's not being swept out because the shape of the object hasn't changed.
This whole thing's being swept out though. So if I do this,
Oh, it covers
and I
more
go,
space.
I'm going to take this little pan right here, and I'm going to go like that. How much space is it covered? I don't know, this much, whatever that is. 37 pi over 4. No, I'm just kidding. Awesome if I could do that. Then how much is this? With the sound effect. Does it sweep out more volume or not?
Because it covers more space.
Of course, it covers a lot more space. It'd be easy if we could just do the same thing, but it's not the same thing. This goes all the way around something that's further away than the x-axis right now. Yes.
So that formula, is it f of x squared or c?
Oh, you know what? I just forgot this.
Oh, so C doesn't square.
No. What did I do to you guys? Goodness me. No, I was right. I was right.
What? Yeah, the C gets squared.
Radius.
Yeah.
That was where I made a mistake. Radius squared and radius squared. I just had too many little brackets. Sorry, I got confused. Radius, hopefully you understand the idea. I didn't just jack it up for you. Good catch, Scott. Radius squared and radius squared. You got it? This is the radius of the inside. This is the radius of the outside. You're squaring it, subtracting them, and times it by pi. That is the surface area of the cross-section of the big one minus the little one. That's what we're talking about, and then we'll integrate that. Let's try to fill this thing out. Where do you start?
Take your constant minus f of x.
Where do you start? Integration. Where do you start? Integration. Sure. It's still 0, right? Still 1. 0 to 1. What do you have inside?
Pi.
Now, inside the pi. You can put the pi on the outside. That's fine. It doesn't really matter. Inside there. What's next? What's our c in this case? Yeah, so when you think about it, it's just 3 halves minus x cubed. Squared, sure. Squared, of course. But that's saying the outside function, that's the larger of the two radii, the outside function, minus inside function, give me that.
3
3 halves.
Hmm? Keep going.
minus x.
Yeah.
Square.
Perfect. I would love it if you would understand where this is coming from. Do you understand where it's coming from? Radius of the outside, big one. Radius of the little one, no problem. This is the surface area after you've subtracted those two things. Can you do the integral? Sure, yeah, sure we can. What's the first step in doing the integral? What would you do?
Deal with our square roots first.
Not square roots.
Or not square roots, excuse me, square.
Yeah. Probably square them. Keeping our signs correct is crucial for you. Also, I'd like to encourage you to start combining like terms if you have them. I don't know if you're going to have them here or not, but if you do have them, my goodness, combine them. Before you start doing integral. Some of you guys are doing integral, you're setting up a problem, and you have like 5 terms, 3 of which can be combined, yet you're doing the integral of all 5 terms. Why? Why? I'm at it. Why? Why not combine your like terms before you do it? It saves you twice the work. It saves you so much work. Okay, I'm off my little soapbox now. Let's go ahead and figure out the rest of this. If I do this, this is 9/4 minus.
I said it was the top minus the bottom.
Say what?
Oh, right, never mind.
You know what? It really is, but you can't see it here. It is the top minus the bottom,
All right.
but it's just a different axis. You just have to set it this way.
Yeah.
Kind of reverse thinking. Outside, inside. Okay, good question. 9/2 minus 3x cubed, I believe. Plus x to the 6th. Very good. That's the first one. Hope I don't run out of room here. Next one gives you 9/4. Notice how it's still in parentheses. I'm not dealing with that yet. I'm not doing it in my head. I'm making sure I have the signs right. Even I do this. Take your time to do the signs right. Minus 3x. Plus x squared. And I need a dx. Don't forget about your dx. It says what you're integrating. Can I get a double check on my work, make sure that I've done that correctly? Yes, yes, yes. Can you see that far? 9/4 minus 3x cubed plus x to the 6th. Then minus, in parentheses, 9/4 minus 3x plus x squared. Yeah, you know what? We are going to do that. We're going to distribute negative. We're going to look to see if we can combine anything after that. We have 9/4. We have minus 3x cubed plus x to the 6th minus 9/4 plus 3x minus x squared dx. I'm going to move over here. Do you have any questions on the picture that I drew firstly? Okay. Wow, okay, so pi 0 to 1. Oh, that's nice. I like 0s to 1s. Those are real cool. What happens here?
Simplify.
This is why you'd simplify before you do an integral, because otherwise you'd integrate 9/4 and you have 9/4 x twice, and you're gonna eventually get rid of those numbers anyway. Why not get rid of them now and don't waste time integrating? The other things, you can't combine any of that. I'm gonna write it in the appropriate order. I'll write x to the 6th. I see a minus 3x cubed. I see a minus x squared. And a, what was it, plus 3x? Can you do the integral? Of course. Yeah, it's actually not bad, right? It's the setup that's hard. It's understanding that. Let's check your integral, check it with my integral, let's make sure we both did them right. Did you guys get it right as well? Same thing? Same? Now we're going to plug in 1 first, we'll plug in 0 next. If I plug in the 1, if I evaluate, I'm going to get 1/7. I love ones too. Man, they're nice. 3/4, 1/3, and 3/2. I'm going to check the 0, but notice how every term is going to go to 0. So I'm going to write at the back end of this, yeah, I did check 0, it's just going to be 0. So far, so good? Notice, please stop for a second. Notice how if the 0 had come first, it would be 0 minus all this stuff. You follow? Making it all negative. That would be the case for the other part of this, the between -1 and 0. You follow? Now, if that went around 3/2, notice that that volume is going to be huge, which is why I almost made the mistake of, remember the odd function, how you just double it? That's not the case for volumes, because you're taking something way lower, way above that 3/2. It's going to be a much larger volume. You'd have to do a completely different integral for that. Do you get it? So we set up the same, but it'd be a different volume altogether. So, combine all those. Has anyone done 1/7 minus 3/4?
Yeah, 89 or 84.
How much?
89 over 84.
I guess something different.
1/7 minus 3/4 plus, minus 1/3. And then, what do I put in here? Make sure I put it in here. Plus 1/3 over 2.
Okay.
I have 47/84.
Okay, you're not doing wrong.
Pi times 47/84 is 47 pi over 84. I gotta be honest. Your calculus, you guys know how to set this stuff up. You're plugging numbers in, not so great. Make sure you plug the numbers in right. That's the biggest mistake I've seen on tests all the time.